Back to the line integral. Today we're looking at the geometric definition of the line integral. Let's go ahead and take a look. So folks, our focus today is on the geometric definition of the line integral. But what is that geometric definition? Today I'll show you in less than 5 minutes. So buckle your seatbelts and let's go ahead and take a look at the geometric definition of the line integral. So here I am on the XYZ plane, and what I'm going to start with is some kind of a path. This point on my path might be associated with this z value. This point might be associated with that z value. Okay, and all of these z values together, they constitute some kind of a function. That right there might be the function that all of these, points, these z values lie on. So for example, that right there might be all of the z values put together into another path. Now connect these two paths and you're gonna get some kind of a fence. So check it out. So how do I find that area? That's the key question that line integrals try to answer. So I'm going to show you how. It's really quite simple. So take a look at this small change. Take a look at that small change in my arc length. Let's call that small change ds. Okay, and let's grab the height of one of these rectangles so we can find one of their areas. Okay, so let's focus on this rectangle over here, and say I want to find its area. Well, I know that this is ds, but what's the height of the rectangle? Well, the height of the rectangle is simply gonna, if I plug the coordinates of this point into my function, I'm gonna get the height of my rectangle. So the height over here is gonna be what? F of x of t comma y of t, right? And of course I'm using t because that might be the parameterization of my path on the xy axis. So that being said, what am I gonna have? The area of one of these little pieces is gonna be what? Okay, the area of this piece is simply going to be the base times its height. So check it out. I know what the base is. My base is simply ds, a differential length in arc length. So ds, and I know what my height is. My height is f of x of t comma y of t. And so putting those two facts together, I know what the area of this rectangle is. It's simply going to be what? What's my area going to be? It's going to be f of x of t comma y of t times ds. But how can I express ds in terms of t? After all, I simply want one parameter, t. So let me show you how. Let's erase this for a moment and let's focus on this ds over here. So if I zoom in on this curve over here, I'm going to get something like that, right? That right there might be my curve. Now this curve we can approximate as a line segment because it's so infinitesimally small, it's basically like a line. And so if this line segment is ds, it can be broken down into x and y components, dx and dy. So that means, what can we do? We can just go ahead and write the Pythagorean Theorem, right? And what does the Pythagorean Theorem tell us? It tells us that ds is simply going to be the square root of the sum of these things, right? So dx squared plus dy squared, right? Pretty simple. And check it out. Let me go ahead and erase this over here. If I go ahead and multiply this radicand by dt over dt, what am I going to end up with? Well, actually I'm going to end up with r prime of t dt, which of course equals dr, right? So instead of ds, I can either write r prime of t dt or dr, up to you. So that means the area of all of these, I can take the summation and take the limit of that summation to finally get the following. The line integral over my path C is going to be f of r of t times let's go ahead and erase that. F of r of t times r prime of t dt, folks. And that right there is the geometric definition of the line integral. Thanks for watching, and we'll see you next time.